So today we continue to talk about strings. Today we talk about suffix array. I have a full lesson about suffix array on code forces you do, so maybe you want to see that, but I will repeat like everything, the same thing in this live lecture, just because this course will be not full without suffix arrays. So we'll talk about suffix array today. So what is suffix array and why you want to use suffix array? Suffix array is very simple data structure. You have some string. Let's say you have some string. Let's say A, B, B, A, and B, A, something like that. And you just write down all the suffixes of this string in lexicographical order. So you start from empty suffix. So first you have the empty suffix. Then you put the lexicographically smallest suffix. Lexicographically smallest suffix is A. The next suffix will be ABA. Then we have ABB. The full string ABB, ABA. Then we get suffixes starting from B. So we have BA. Then we have BABA, not very interesting. And then we have this suffix, so we have BBABA. 6 and 6, yeah. So these are all the suffixes of this string S in lexicographical order. That's all. This is the suffix array. This is what we want to build today, and yeah, that's all. So first of all, how to store the suffix arrays? You don't want to store suffix arrays as an array of strings, because the total size of all these strings is n squared basically. So it's sum of all i's from I to n, from 1 to n. So the total length of all these strings is n squared, and that's too much. So instead of storing all the suffixes, we want to store only the indices of these suffixes. So instead of storing this suffix, we will say that this is not a string, but this is the suffix of the string S starting from this letter. So we will enumerate all the characters from left to right, like usual. So we'll say 0, 1, 2, 3, 4, 5, 6. 6 is just the end of the string. And now you just, instead of writing down the suffix itself, you just write the first index of the first letter of the suffix. So this is the suffix starting from letter 6. So it's just the empty suffix. Here the suffix starts with the 5. Here you start from the third letter. Here you start from the 0. Here you start from here. So it's 4. Here you have 2 and 1. Why does suffix not A, B, B? We don't have suffix AB here. Suffix is the end of the string. So there's no suffix. Array of prefixes is pretty simple. You can do it by yourself. If you just want to have all the prefixes of the string, it's pretty simple. You can do it by yourself. So it's the idea is the array of suffixes. It's very easy to sort all the prefixes of the string. Okay, you can do it. But the sorting of the suffixes is slightly more complicated idea. Okay. That's all. So you have this array P. This array P is the array you want to build. So this array P represents your suffix array. And if you look at this array P, it's actually enough to get any information about these suffixes. For example, you want to take, so you don't know these strings, yeah? You only have these indices. And you want to have some character from one of the suffix. For example, you want to take this suffix and take this third letter of this suffix. So how to find the third letter of this suffix if you don't know these strings? You just look at this index. So the first index of this suffix is 2. So index of this letter is 2, index of this letter is 3, index of this letter is 4. So this letter is actually the fourth letter of this string S. So you go to the string S, take the fourth letter of this string S, and just return this letter. So you can, in constant time, you can get any character of any suffix from just using this array P. So if you take a suffix of number I and one letter of with index J, so it will be S like PI plus J. So PI is the index of the first letter, plus J is index of this letter. So you just look at the corresponding letter in string S and just take this letter. Yeah. Just wait for it. We'll talk about it in a second. Why you may want to use this suffix array? There are multiple problems can be solved by suffix array. The easiest problem, like not the easiest problem, but one of the most common problems you want to use using suffix array is the problem of substring search. Again, we come back to the suffix search problem, or to the substring search problem. Imagine you have some text and you want to find some substrings in this text. It's like a very common problem. You have something like, I don't know, you have like the library and you want to have some index in this library. So you're given some word and you want to find this word in your library. Or you have like a website and you want to have index in your website. So the user types something in the search and you find this string in the website, something like that. So it's quite common problem to find some substring in the given text. And we know how to solve the problem. We know how to solve this problem in linear time, yeah? But here we have slightly different problem. We have the text and we have multiple queries. So we have some text and we have multiple queries, let's say. I'm out of letters, okay. So it's P1. Let's make it Q, just to not mess with array P. We have multiple queries. First query, second query, third query, and so on. And for each query, we want to find this string in the text. So for each query, we want to find this string in the text. Yep. And we know how to solve this problem using a Karasik algorithm from the previous lecture. So if we have all these requests, we can find all the strings in the text in one pass, right? So using the Karasik algorithm from previous lecture. But if you don't have all these queries beforehand, someone is giving you these queries one by one. So first he asks you to find this string, then this string, then this string, and so on. So you have multiple queries, and you need to answer them one by one. You can't answer the next query before you answer the previous query, right? That's how it usually happens here. Someone asks you to find this string, then asks you to find some another string. And he don't want to wait. So to give you all requests before you start your search. Yeah? So for a problem like this, we can use the suffix array. So what we can do? We can build the suffix array for this text. So we take this text. Well, let's change it with S, just to match this. Okay. So we take this text and build the suffix array for this text. And now, using the suffix array, we can easily find all the substrings, because any substring is a prefix of some suffix, right? Like we discussed in the first lecture about strings. Yeah? So this substring is prefix of this suffix. This suffix must be in your suffix array. So we just need to find some suffix which starts with the given string Q. How to find the suffix which starts with a given string? For example, let's take this text and try to find something, I don't know, something ABB. So we have a query ABB. Too easy. No, well, good enough. So what we need to do? We need to find a suffix which starts with letter A, B, B, right? So how to do it? We can do it using binary search. Since all the suffixes are sorted, we can just make binary search and find the first suffix which is greater than ABB. So we just take this ABB and find it here using binary search. We will find this place. Yeah. So this string is less than ABB. This is greater or equal than ABB. And that's all. So now I claim that the first string which is greater or equal than ABB must start with ABB. If we have any string starting with ABB, so it must be the first string which is greater or equal than S, than this. So we just make binary search, trying to find this string Q in our suffix array. We'll find this position and the next string, this string. If there is any suffix which starts with the given string, it must be this suffix. Because it is lexicographical minimal suffix which is greater or equal than string Q. Yeah? So we just check this suffix and we see it actually starts with ABB. So we find the string ABB in our text. And we know its position, because its position is just the index of this suffix. That's all. So we can answer these queries using binary search. Binary search actually works in time. Time complexity will be log n multiplied by the time we need to compare to strings. Yeah, we compare to strings in time proportional to the length of the string. Yeah, so we need to multiply this log n by the length of the string q pi, something like this. So we can answer the queries in almost linear time. So it will be linear time multiplied by the logarithm of the length of the text. Logarithm is usually pretty small. There is a way to do it faster, actually. If you pre-calculate some more information about your suffixes, you can do it in log n plus length of the string, but usually it's enough. The power of this data structure is it is very compact. So the size of the data structure is pretty small. All you need to have is this array of integers of the size of your text. So you have the text of size, I don't know, 1,000,000 characters. Now you need one more array of 1,000,000 integers. That's all. That's enough to answer these queries. So it's very memory efficient, right? Tree on reverse tree, no, it's slightly different. So we have, instead of prefixes, we have suffixes, but we don't reverse them. If you reverse the suffixes, you will have another order of the suffixes. No, the idea is, no. The idea is you take suffixes, so you have some endings of your strings, yeah. But when you compare the suffixes, you go from left to right? So you have suffixes like the endings of the string, but you compare them from left to right. So you kind of compare the substrings. That's what's happening. So all the prefixes of these suffixes are all your substrings. So it's like compact representation of all the substrings of the given text. No, it can be done. It can be done easily. Like if you just reverse the string and do something. When you reverse the string, you need some order which goes from right to left. It's like the same problem. Okay. Nice. So that's one of the most common problems which can be solved using suffix arrays. There are other problems, like the problems about suffix arrays and other suffix structures. We will talk about suffix trees next week. All the suffix structures are used when you need to calculate something about substrings of the given text. So you have a text, and you want kind of to analyze something about all the substrings of the given text. So these suffix arrays somehow compact representation of all the possible substrings of the given text. So all the substrings of this text is just all the prefixes of these suffixes. So if you look at all the prefixes of the suffixes, you will get all the substrings. And you want to, and since they are sorted, you can implement some efficient algorithms to analyze them. Is improved complexity but computes the same characters in two consecutive. What? I don't get it. Don't get your question. Complex to computing the same characters in two consecutive elements. Extreme. No. If you want to do it faster, you need kind of to pre-calculate all possible ways of your binary search. So for all, you can do it as an exercise. Yes. No, because when you do the binary search, you kind of compare the same characters from left to right. If you compare the first k characters and know they're equal to this string, then when you go to the next branch of your binary search, you kind of want to skip all these first characters because you know these characters in the previous stage of the binary search, they were equal to these characters. So you kind of, on the next stage, you kind of want to skip them and so on. Yeah, the idea is to pre-calculate something which allows you to skip all the characters which you already compared before. You may think about it as an exercise. Okay, I will not discuss today. What we'll discuss today is how to build this suffix array. So this lecture will be about how to build this suffix array. Well, first, let's discuss some simple algorithms. For example, what you can do, how you can calculate suffix array. You can just write this array of all suffixes and sort them. Yeah? Also, this is sorted array of suffixes. You can write down all the suffixes and sort them. Why not? What's the problem? Yeah. No problem, actually. Let's just remove this. So the first idea, let's just write all the suffixes and sort them. Not the suffixes themselves. Again, you don't need to write all the suffixes themselves. Let's make array P, just put them integers from 0 to n, then sort this array P with comparator which compares two strings. Yeah. Just sort. What will be the time complexity if you just take all the suffixes and sort them? No, the complexity of sorting algorithm is n log n. But in each stage of the sorting algorithm, you need to compare two strings. Yeah. So this n log n will be multiplied by the time complexity of the comparator. Let's just put it multiplied by comparator. Yeah. No. We'll go too fast. I will do it in a second. First of all, if you just compare two strings like you usually do, just go from left to right until you find the first. So how to compare two strings again? You have two strings. You go from left to right and find the first character which is different. So these characters are the same, and this character is different. Here you have x, here you have y. So you check this x is less than y, and then so the whole string is less than this string. That's how you compare two strings. So if you just implement it like this, in the worst case, you may, in each comparator, you may go up to the end of the string each time. So the complexity of this comparator may be linear. So if in the worst case, you will have something like this. You will have n square log n. That's obviously too much. Yeah. But actually, in some cases, it's a legit algorithm. So in some cases, if your string is pretty random, in some sense, yeah. If your string is pretty random, for example, you have something like, I don't know, for example, you have some DNA string, yeah. So you have a DNA sequence. DNA sequence is pretty random. There are some blocks of equal data, but pretty much random, yeah. So if you have some random string, then the complexity of comparator is actually small. No, since if you have completely random strings, then the probability that you have a long common prefix is pretty small. No, so the probability that you have k equal characters will just decrease exponentially, right? So usually the comparator will work in constant time if you have random string. So for random strings, it's actually a good strategy. What's best about this strategy is that you don't need any other arrays. You just make this array P, then run a sorting algorithm on this array P, and in the end you have a sorted array P. That's all. You don't need any other arrays. So it's absolutely optimal if you think about memory additional memory. Yeah. So if you have very small amount of memory and a random string, that's the best you can do. But in the worst case, yes, in the worst case it is pretty slow. So how can we improve it? We can, yes, we can use hashing from the previous lecture, from the 2 weeks before. So we can use hashing algorithm. So we can compare. So again, to compare two strings, we need to find the maximal common prefix for these two strings. And to find the maximal common prefix, we can use binary search with hashes. So we can find this length of this common prefix using binary search. And when we compare two strings, we just use hash. Yeah. So we calculate hash of this string, hash of this string, compare them. If they're the same, we go to the left, to the right. If they're different, we go to the left in the binary search and so on. Yeah. So we just make a binary. So each time we need to compare two suffixes, we use a binary search. And inside this binary search, we need to compare two strings, and we use hashes for this. Yeah. So we use hashes plus binary search. So the complexity of comparator will be log n. So if you use binary search and hashes, then each comparator will work on log n time. So total complexity will be n log square, like this. This is also a legit algorithm. You can implement it like this. Not very efficient, but actually quite good. It has two problems. First of all, we need to use hashes. And we need to just believe that we have no collisions in these hashes. So we need to have some big hash, good hash, so there will be no collisions. Because any collision will break your sorting algorithm. If you have any collision, then you will have wrong result in your binary search. You will have wrong result for your comparator. Any collision may completely ruin your sorting algorithm. So if you compare two strings and you have the one wrong result in this comparison, will just break all your sorting algorithm. It's not good to break sorting algorithms. So it's good enough algorithm, but we will do better. Another problem with this algorithm is use n log square time. It's n log square plus hashes. When you use hashes, you need some modular arithmetics and stuff. So it's actually pretty slow. We will make fast algorithm, but good enough. It's much better than just using standard comparator. If you have some bad cases, what's bad case? Bad case, for example, if you have some, if all characters are equal, you have string of the same letter, very long string, then the simple comparator will just go across the whole string each time. So this will be much better, but we will make. Okay, I talk about this algorithm too much. Again. How to compare two strings using hashing? How to compare two strings? We need to find the maximal common prefix. So we compare these characters and then find the first character which differs. Yeah. So we need to find the maximal common prefix of these two given strings, and then check the next letter after this common prefix. So we can find the longest common prefix just using hashes plus binary search. So we make binary search and find the maximal number of characters we can take from here to here, so these strings will be equal. So we calculate this hash, and compare them. If they're equal, we moved our binary search Yep. So we use binary search to find the longest common prefix. And inside this binary search, we need to compare the strings. Just we need to check if the strings are equal or not, and we can check the equality of two strings just using hashes. Nice. So let's go to the algorithm. Okay. Now let's move to the real algorithm. So now we'll talk about the main algorithm. Go. So the easiest way to explain this algorithm is to modify the problem a little bit. Yeah, we'll do. Yes, just wait for it. We will do it. We'll do it in a second. Go. So you can implement the algorithm just without all these first action, but it's a little bit easier to understand what's going on when I modify the problem a little bit. Actually, it's you can do it without it, but it's easier to understand when I do it. Okay, so I'll do it. Let's modify a problem. Okay, let's go. Okay, you'll see. So I want to modify a problem a little bit to make it a little bit more easier. Okay, so first of all, what's the problem? First problem is all the strings have different length. So I need to sort the strings, and the length of all strings is different. That's not very comfortable. When you have strings of different length, you may accidentally ask for some character and there is no character. So it's a little bit uncomfortable. So I will make all the strings the same length. How to make all the strings the same length? First of all, let's put the special character in the end of the string. So first, put here special character. This special character will be less than any character of the given strings. So if you just put this in, then all the suffixes will be extended this character. Yeah? Like this. Yes, in practice you can use zero character. Actually, in C++ you have zero character in the end of the string, so it's quite useful. Yeah, but it's hard to write zero character on the whiteboard, so I will use $sign. Okay, so this $sign is a special character which is less than all the characters of your string. Now let's see. If I add this special character in to all the suffixes, the order of the suffixes will not change. Yeah, so the order of the suffixes will be the same. Well, because when you compare two suffixes, you compare them from left to right. If you compare this dollar to something, it will be less than something, and that's what you need. Yeah. So if one string is a prefix of another string, it must be less. So if one string is less than another string, then when you add the special character in the end, it will still be less than this string. Yeah. Again, you have two strings, and this string is less than this string. If you add this $sign to this end, yeah. Let's say A and B. If A was less than B, then when you add this $sign to both strings, A will still be less than B. Well, because if A was less than B, it means it has either some common prefix here plus some characters here. So in that case, A is still less than B. Or it may be a prefix, so maybe it was A and B something like this. So if A is prefix of B, it is lexigraphically smaller than B. Like here, we have A and then ABA. Right? And here BA and then BABA. But if you add this $sign, it will still be less, because when you go from left to right, you go to this $sign. $sign will be less than this. So this modification will not change the order of the suffixes. So it's good. Okay. Now what we need to do? Using this $sign, we can extend all the letters to make them the same length. And for technical reasons, the easiest way to do is to write all the same characters from left to right in the same string. So after the $sign, let's write all the letters from left to right again to make all the strings the same length. So for example, here we have A, B, A $, and then we go from here again and say right, A, B, and B. And now do the same to all other strings. So we have here, you have A, B, B, A. Here we have A. No, must be AB, right? AB. Slightly not lined. Okay. So here we have A, B, B, A, B, and here we have A, B, B, A, B, A. So now we have, instead of suffixes, we have a cyclic shifts of this string, right? So now all these strings are the suffix shifts of this string S. So again, what does it mean? We have string free. String free, it means we start from this letter free, from here, and follow the same characters to the end, and then start from the beginning to the characters. So now instead of suffix, we have string from here to here, then we start from the beginning and start from here to here. And we get this string, this string. Okay, it is more comfortable because we have now all the strings have the same characters. Yeah. For some, again, for technical reasons, you can avoid all these transformations. You can do the same algorithm just for your suffixes, but you will have more conditions. Sometimes you need to check that you go to the end of the string and something. So you will have more conditions. That's just more easier way to understand what's going on. Okay. Now after these modifications, we have all the cyclic shifts like this, and we need to sort all the cyclic shifts. It's little bit easier. Okay. Now finally, the length of the string is not power of 2. Again, it's not good. Okay, the length of the string is... I forgot something. So it must be here, right? Maybe like this. Yeah. So the length of all strings is 7. 7 is not power of 2. And I want the length of the strings to be power of 2. So let's add one more character to all the strings. So I will add one more character to all the strings to make all the strings the length equal to some power of 2. And the next character again will be the next character in the cycle. So I will continue to write down the characters in a cyclic way. So the next character will be $, here. Here will be A, B, B, and B. And now the length of the string is power of 2. That's all. Again, we want to sort the suffixes. Yeah? But suffixes are strange. Suffixes have different length and so on. So what we did, we just add this $sign to the end of the string, and then added some more letters in the cycle. So the total length of the string will be a power of 2. So now instead of sorting the suffixes, we need to sort strings from S I to I plus 2 power of k minus 1 in cycle. So if we sort these strings, we will have the sorted array of suffixes, because the order of suffix is the same as the order of these cyclic shifts. That's all. Whew. Let's go. Now we just build this. So the algorithm will contain several phases. On a phase K, so I'll just write down the same thing. I will increase this value of k from 0 to log n. So in the end, I will have the sort array of strings. So in phase K, I will sort strings again. I just run the same thing. 2i plus 2 power of k minus 1. So let's start with k equal to 0. So if k equal to 0. So what's going on with k equal to 0? If k equal to 0, it means I need to sort the strings of size 1. Okay? So I need to sort strings s from I to 2 in power of k is 1. So from I to I. So in the 0 phase, you just need to sort all the strings of one character. You can sort strings of one character using any sorting algorithm. Okay? So you just write down all the characters of your string and sort them. So you sort all the single characters. You can do it in n log n time using any sorting algorithm. Yeah, you can use merge sort, you can quick sort, heap sort. Heap sort is not very efficient with infraloxing, but yeah, merge sort, quick sort are basically all you need. Now I will make a transition. I will make a transition from k to k plus 1. So in the phase k, I have sorted strings of length 2 in power of k. So on the next phase, I need to sort all the strings of length 2 in power k plus 1. Okay. How to sort strings of the length k 2 in power k plus 1? I will just sort them using sorting algorithm. But to implement the sorting algorithm, I need to first comparator. I need to compare two strings of the length k plus 2 in the power k plus 1 first. Yeah. So let's see. I need to make a comparator which takes two strings a and b and compare them. Yeah. So let's see. So if a is so how to check if a is less than b? So if you have two strings of length 2 in the power of k plus 1, how you can compare two strings? Well, like usually, you will divide this string into two strings of length 2 in the power of k. Yeah. It's basically the same principle we used in all the data structures, in segment trees, in binary climbing when we discussed tree algorithms and so on. So I'll just split this long string into two smaller strings. So all these smaller strings have length 2 in power k. Yeah. And now I have strings of length 2 in power of k. And in the previous phase, I already sorted all the strings of the length 2 in power of k. So I know some information about the strings. So now what I need to do? Let's see. So if these two strings, so this is A1, this is A2, this is B1, this is B2. So if we know how to compare strings of length 2 in the power of k, how we can compare two strings of length 2 in the power of k plus 1? It's easy. We need to compare the strings A1 and B1. So if A1 is less than B1, then what does it mean? It means we have some common prefix here, and then some character here, some character here. So this is less than this. So if A1 is less than B1, then the whole string A is less than string B. Right? So again, we have the same common prefix and the same character here. So if A1 is less than B1, then A is less than B. Now, if A1 is equal to B1, if we have two equal strings here, then we need to compare A2 and B2. So we follow here. We have some character here and some character here. So we need to compare strings A1 and B1, and if they're equal, we need to compare A2 and B2. So the comparator looks like this. So A less than B is the same as A1 less than B1, or A1 equal to B1 and A2 is less than B2. So we have a comparator like this. What does it mean? It means that if we can compare strings of length 2 in power of k, then we can compare strings of 2 in power k plus 1 in constant time. So if we can do, if we can make these comparisons in constant time, so like this comparison, this comparison, this comparison. So if we can do all these comparisons constant time, then we can compare the strings of length 2 k plus 1 in constant time. You may think about this as comparing two pairs. So if you have, so actually it is the same as comparing two pairs. So we need to compare pair A1 B1 with pair A2 B2. Yeah. Again, when you compare two pairs, you compare the first element of the pairs. If it is the same, you compare the second element of the pair. Yeah. Now, how to compare two strings of length 2 in power of k? Now, we will use the result from the previous step. So in the previous step, we already sorted all the strings of length 2 in power k. So we have the sorted. So we have the sorted array of strings of length 2 in power k. So strings A1, B1, A2, and B2 are in this array. So in the phase k, yeah, we already have this array. Yep. So we have the sorted array is less A1 B1 less than A2 B2. Yes, that's what I write. Yeah. Yeah. So this pair is less than this pair as pairs. Yeah. Now, so again, in the previous step, in the step k, we have this array of all the possible strings of length 2 in power of k. And we have it in sorted order. So, how to compare two strings if we know their positions in this array? So, for example, you know that position of string A1 is here, and position of string B1 is here. Okay, my bad, my bad. No. You know what I mean, okay. A1, B, A2 less than B1, B2. Yeah, my bad. Thanks. I just tried it from here and okay, my brain can okay, it happens. Yes, thank you again. Okay, now back to here. So I want to compare two strings of the length 2 in power of k. Yeah. I have both these strings in this array. So this is the sorted array of strings of length 2 in power k. So how to compare these two strings? No, since the strings are in sorted order, yeah, we can look at the positions of these strings in this array, and the string below must be greater or equal in this string, right? Well, since the array is sorted, yeah, the string in the bottom must be greater than the string in the top, or equal. This or equal is important, since we don't know actually. So if we have just two positions, this B1 may be greater than A1, or it may be equal to A1. And we actually have the strict equation here. So we need to check if it is less or if it is equal. So if A1 is below B1, it's definitely not less, right? But if it is above, it may be less or it may be equal. And we need to distinguish these two cases. So they have the following problem. We have the strings. Well, let's put, for example, let's take this string again. So, for example, we have this string, and we already completed phase 1. So we completed phase 1, and we know these strings. We have A, we have A dollar, we have AB, AB, BA, BA, and BB. So if we have this string, then after phase 1, we have this array. Not as array of strings again. It will not be array of strings. It will be array of indices, but it doesn't matter. So we have this array P, basically 6, 5, something like 0, 3, 2, 4, and 1, something like that. So after the phase 1, we have this array P. Now, we want to be able to compare the strings. So we want to check, for the given two strings, if the strings are equal or not. We can do it just by enumerating all the equal strings to with the same number. So we'll go from top to bottom and assign a number to each string. This number will be the same for the equal strings, and for different strings, the less string will have less number. So, you got it. Okay, so we just go from top to bottom and assign the numbers from 0. So we assign number 0 to the first string. So these strings are different, so we assign the next number. So we have number 1. So these strings are different, so we assign number 2. These strings are equal, so we assign the same number. These strings are different, so we assign next number. These strings are equal, so we assign number 3. These strings are different, so we assign number 4. So we'll build this array C. And now we just use this array C to compare these two strings, A1 and B1 and A2 and B2. Again, to compare two strings, we just need to compare these numbers. If number is smaller, then the string itself is smaller. For example, again, you want to compare some strings. Let's compare something. Let's compare these two strings. Right. So we have string in position 4 and in position 2. So we have string BA $A and string BA BA. So these are strings in position 2 and 4 and 2. So in the next when we move to phase k equal 2, we need to compare these two strings. So these two strings can be split into two strings of size 2, right? So we split these two strings into two halves, these two strings into two halves. Now, each of these strings we need to find in this array. Now it's easy, we know the positions. So this string is in position 4. So the first half is in position 4. We find position 4 and know the integer here is 3. So it's like the class of this string. Let's call it class of this string. So the class of this string, it will be 3. Let's find this string. This string is $A. It's here. So $A has class 0. So the second half has class 0. How can we find it easily? No, we know the position of the string is 4. So the position of the second half will be 4 plus 2. So the position of this string is 4. Position of this string is 6. So we find string 4. So this string will be A1. This string will be A2. Again, we can find just by using these indices. We know the index of this position is 4, so index of this position must be 6. And now in the same way we will find the positions of these two strings. So this string has position 2. So this string must have position 4. So this string will be 2, it's here. It has class 3. and the second half is in position 2, in position 4. So it's here. And he's also 3. And now we just need to compare these two pairs. We need to compare pair 3, 0 with the pair 3, 3. We know that 3, 0 is less than 3, 3. We can do it in constant time, just comparing these integers. So we compare these two strings. So we know that 3, 0 is less than 3, 3. It means that this string is less than this string. That's all. So again, the algorithm. We go in different stages. So on each stage, we have this number k, and we want to sort the strings of the length 2 in the power of k. And in stage 0, it's simple. We just need to sort all the strings of the single characters. We can do it using any sorting algorithm. Now, when we move from stage k to stage k plus 1, so we take the previous stage, take this array P, calculate this array C. So this array C will assign some numbers to these strings so that the smaller string has a smaller number. Now we use this array C to make this first comparator. So this first comparator works like this. It takes these two strings, look at the first half of the strings and look at the second half of the strings. If this first half is the same, then it compares the second half. How to compare these two strings? These two strings are the strings of size 2 in the power of k. We can find these strings in this array just by using these indices. We don't need these strings. We only need these indices, right? So we have only these two arrays of indices, of integers. So we find these two strings in this array, find the corresponding classes, and find these two strings in this array, and find the corresponding classes. And now we just need to compare these two pairs of integers. We can compare this pair of integers in constant time, so the comparator will work in constant time. Ta-da! That's all. What will be total complexity? Total complexity will be like this. So first of all, we need to sort the, let's write total complexity. So first we spend n log n time to sort, to make phase 0, and now we make log n more phases. In each stage we make this, we run the sorting algorithm. So in each stage we resort the array P. Each sorting costs you n log n time. So total time complexity will be n log square. It can be easily improved to n log n. It can be easily improved to n log n time just by removing this sorting algorithm here. So the critical part here is this sorting algorithm. Every time we run the same sorting algorithm again and again. We can avoid the sorting algorithm just by looking at what actually we're sorting. We're sorting not some random objects. We're sorting the pairs of small integers. So each time we sort the pairs like A1, A2, now I make it correctly, and pair B1, B2. And both these pairs contain only small integers. So all these integers, A1, A2, B1, and B2, are from 0 to n minus 1. Yeah. So we need to compare not something, we need to compare pairs of small integers. We can compare pairs of small integers using radix sort. If you forgot how the radix sort works, so we discussed it like last year in the first semester. Basically, you need to run this counting sort twice. So you need to run counting sort for the second part of your pair, and then again run the radix sort for the first half of your pair. And after two passes of this radix sort, of the counting sort, you will have the sorted array of pairs. Yes, you can build suffix array in linear time. That's true. You can do it, but the constant will be bad. So it will be linear, but the constant factor will be greater than this, and actually what's more important than the memory you need to use in the linear time algorithm is much larger. So you can do it in linear time. It's not that interesting because you can actually build the suffix tree in linear time. So for theoretical use, the suffix tree is actually much more interesting than suffix array. But for practical use, this algorithm is more interesting because linear algorithm is actually usually it's slower, and it is actually it uses much more memory to build this suffix array. So usually this algorithm is more efficient. That's what I mean. Yes, if the size of alphabet is up to n, then you can do it in linear time. Yeah, right. No. So no. But you need sorted you kind of need sorted alphabet. So you need to be able to sort the letters. Yeah. Okay, if instead of letters you have integers from 1 to n, then you can do it in linear time. Let's say it like this. Okay, now let's run this example. Let's just run this algorithm on this string just to make everything clear. Okay. So I will just take this string and run the whole algorithm just so you understand completely what's going on. Is it enough? I think not. I need to erase this. Okay. Yeah, that's true. You actually don't need linear time suffix array algorithm because you can build suffix tree in linear time and then convert it to suffix array. That's true. Alternatively, you can build a suffix tree and then convert to suffix array and then convert suffix array to suffix tree. That's also possible. It's just different ways of building the same thing. Basically, all the suffix structures, I believe, can be transformed one to each other. So then, not that different. All the suffix structure basically do the same thing. Go. So we take this string and try to build the suffix array for this string. Let's remove everything, not important here, and this. We start from the phase k equal to 0. So we start from k equal to 0. In the phase k0, we need to sort the strings of the single characters. So we just take this array of characters, so we just sort them. So we have this array $, then A, then B, and B. Again, we never store this array of strings. I just write these strings just for clarity. You don't need this array of strings. You only need the array of indices. So you make the array of indices. Indexes of this will be 6, 0, 3, 5, and for B's it will be 1, 2, and 4. So we have this array P. So this will be array P from the stage 0 of your algorithm. Now we calculate the array C. Array C will be array of classes. So we want to assign integers to all the strings. So the smaller string have the smaller integer and so on. So again, you go from top to bottom and then assign these integers. So it's here integer 0, 1, 1, 1, 2, 2, and 2. and this would be your array C. Well, let's discuss suffix trees next week, okay? Okay, let's keep concentrated here. We'll talk about suffix trees next week. I promise. Now, that's all. Now we finished the stage 0. Now we move to stage 1. So we move to stage k equal to 1. In stage 1, we need to sort strings of size 2. So we have all the strings of size 2. I'll just write down all the strings of size 2. So I have strings AB, BB, BA, AB, BA, $A, and then $A. So the indices will be 0, 1, 2, 3, 4, 5, 6. Now for each string, I want to make a pair of two integers. So first integer will be the class of the first half, second will be the class of the second half. I take the first string, so I have the string of size 2 in position 0. It means it contains strings in position 0 and 1. So string in position 0 has class 1, string in position 1 has class 2. Yeah? So again, let me use something lighter marker. So I have these two strings. This string is position 0, this in position 1. String in position 0 is here, string in position 1 is here. I'm not sure if you can see it, but so the class of the first string is 1, of the second string is 2. So this string corresponds to pair 1, 2. Okay. This string contains strings in position 1 and 2. So this in 1 is 2, in 2 is 2. So it corresponds to pair 2, 2. And so on. For each string, again, you don't need this array of strings. You only need this red array of P and this array of pairs. So you just write down all this array of pairs. So you have this array. So BA is 2, 1, it's 1, 2, 2, 1, 1, 0, 0, 1. And now I just take this array and sort it. If you sort this array, what you get? Okay, so first you get 0, 1. So in position 6, you have 0, 1. In position 5, you have 1, 0. Now in position 0 and 3, you have 1, 2. No. Now 2 and 4, you have 2, 1, 2, 1. And finally in position 1, you have 2, 2. So we just sorted all the strings of size 2. So this will be the array P in iteration 1. Now let's recalculate this array C. The array C will be an array of classes. For each string we need to assign some class to this string. So again, we just go from top to bottom and assign new integers to this string. Again, if strings are equal, we assign the same integer. If they're different, we assign different integer. So we just go from right to left. So this is 0, 1, 2. These are equal 2, different, equal, different. So this will be the final array C. That's all. That's the end of phase 1. So in the phase 1, we build these arrays, sort them, and build array C. So that's all. After the end of phase 1, we have these two arrays. Now let's move to the next phase. So again, in the next phase, let's try to do it without these strings. Okay. Let's just write down all this array of integers and don't use this array of strings. Okay. Let's write down all the strings of length 4. So of length 4 we have 0, 1, 2, 3, 4, 5, 6. Now for each string of length 4, we need to split it into 2 halves again. We have this, so string in position 0 is this string. We need to split it into 2 halves. It will be this and this. Yeah. They have indices 0 and 2. So we need to find string 0 here, it's here. And string 2, it's here. So the class of string 0 will be 2. Class of string 2 will be 3. So here we have pair 2 and 3. That's all. And so on. For string 1, the first half will be 1. The second half will be 3. Because you have shift 2, right? So the first half has position 1, second half has position 3. So this will be class 4 and this will be class 2. So we'll have class 4 and 2. Next one will be 2 and 4. Okay. So 2 will be 3 and 4 is 3, so it will be 3 and 3. Now 3 and 5 it will be 2 and 1. 4 and 6 will be 3 and 0. 5 and 0. Again, now we have cycle, yeah? So string in position 5 is this one. So we start in position 5, go here and then here. So the indices will be 5 and 0, right? So we take string 5, 1 and 0, 2, so it will be 1, 2. And finally here for 6, it will be 6 and 1. So 6 is 0 and 4. That's all. And now we sort this array of pairs. Again, we build this array of integers just using this array of integers. So we just, let me write. So let me take some string. So how did we build these strings? 3. We take the first half and the second half. First half is have index 3, second half is index 5. So we take this 3 and this 5 here. And so on. And now just sort this array. So when we sort this array, we get we get 0, 4 in position 6. Then we have 1, 2. 1, 2 in position 5. Then 2, 1 in position 3. Then 2, 3 in position 0. Then 3, 0, right? Then 3, 0 in position 4. 3, 3. Yeah, 3, 3 in position 2. And finally 4, 2 in position 1. That's all. That's our new array P. And now we rebuild array C. So we need to assign next classes for the strings of length 4. So again, we just go from top to bottom and assign the classes. If strings have the same classes, we assign the same. If strings are equal, we assign the same class. If strings are different, we assign the next class. So again, we go from top to bottom and say this class is 0, they're different, these are different. No, they are different. So we just say like this. This will be array C. Now, finally, if at some point of your algorithm you have all the classes, if all the classes are different, it means you can stop the algorithm. Because you already compare all the suffixes and all these prefixes are different. Yeah? Because you take the first 4 characters from each of these strings and they are all different. If they are all different, you don't need any characters to write. Yeah? So you can stop the algorithm here and return this array as a result. Let's just check it is the same as here. Yeah, so this array is the final array P. So it will be your suffix array. Nice. Okay, I will not write the code. Okay. If you want to look at the code, you can check my code forces lecture. I write the whole code and I actually solve some problems about suffix array there. I will not do it here again. So I believe this is enough. Let's talk about Let's talk about one more algorithm. You stop saying everything is clear. It hurts me. Now, one more thing I want to discuss is for some problems, building suffix array is not enough. So for suffix array is enough for many problems. Thank you. Thank you. Don't need to scream. Yes. Just say it every 30 seconds. It will be enough. Okay. So for some problems it's enough, but for many other problems it's not quite enough. What you need in many problems is to find the longest common prefix for the given two suffixes. So one of the most useful thing you want to calculate with the string is to find the longest common prefix of two given string. Get LCP of string, let's say A and B, is just the maximal case such that string A from 0 to k minus 1 is the same as B from 0 to k minus 1. So basically you take this string A and B, and find the maximal number of characters in the beginning of the string that is also. So we have these characters. There you go. Yeah. That's very important query. It's used in many other problems. So in many other problems, at some point, you want to check the longest common prefix of the two given strings. I'll not discuss today, but there are many applications of this result. So now, instead of calculating longest common prefix of strings, I will calculate longest common prefix of two given suffixes. So here I will implement LCP of I and j will be LCP of suffixes from I to n minus 1 and from j time, like this. Why it's usually enough? No, since if you have many different strings, so if you have requests for different strings, you can just concatenate all your strings, all the strings you need in one big string. So if you have multiple strings, you have S1, S2, S3, and so on. If you want to check longest common prefix of some substrings of this, you can just concatenate them all in some long string S, then calculate suffix array for this long string. And now if you want to calculate like LCP for this and this, you take this suffix and this suffix and just calculate LCP of these two suffixes. So calculating LCP of suffixes is usually enough for most of the problems. So I want to solve the following problem. I have a given string and I have multiple queries. Each query is to find the longest common prefix of two given suffixes. So someone is giving me two suffixes and I need to find the longest common prefix. That's all. So someone gives me two suffixes, like this suffix and this suffix. And I just say that these two suffixes have two common characters here. So I have AB here and AB here. So the result will be true. Now, let's go. So, how to solve this problem? So to solve this problem, let's find these two suffixes in a suffix array. So we know the indices of these two suffixes. We can find these indices in array P. So we take these indices I and j and find these two numbers in array P. We can pre-calculate for each number its position in array P. It's already calculated in array C actually, but it doesn't matter. So we find these indices I and j in array P. So this will be I, this will be j. And now we do the following trick. So imagine you have the suffix array. You have, this is I, this is j. These two suffixes have some common characters. So these first k characters are the same here and here. Let's look at all suffixes in the middle. So let's look at all suffixes between these two suffixes in the suffix array. So you have some other suffixes here. So have these suffixes, and so on. Now, since the suffixes are sorted, if you have two suffixes with the same prefix, all suffixes in between must also have the same prefix. Because that's how the sorting works, right? So all these suffixes also have this prefix. So what we'll do, instead of calculating the longest common prefix between this and this suffix, we will calculate the longest common prefix between any two consecutive suffixes. So we'll calculate LCP of these two suffixes, LCP of these two suffixes, LCP of these two suffixes, and of these two suffixes. So we will pre-calculate array, say L. Li will be LCP of two suffixes P, let's say I, and Pi plus 1. So let's pre-calculate the following array. So we'll pre-calculate the array L such that in position L we have LCP of two consecutive suffixes in the suffix array. Now, if we know the LCP of these two suffixes, LCP of these two suffixes, of this and this, how can we calculate LCP of the first and the last suffix? Okay, say something. Say something. Again, you have a sequence of strings. You know LCP of these two strings, of these two strings, of these, and these strings. And you want to find the number of common characters in the first and last strings. Yes, you just take the minimum of all these values. So LCP of these two strings will be the minimum of LCPs of this segment of the array. So we need to find the minimum in the segment of array L. So LCP of I and j will be the minimum L T for T going from not ij, so ij is the index, so we need to position I to position of j minus 1, something like that. So we need to find the position of the suffix I, position of suffix j, and between them find the minimum in this segment. So how to find the minimum in the segment of array? You can use segment trees, you can use sparse tables, you can use all this Farah-Colton-Bender algorithm we discussed in the previous semester. So there are many ways to find the minimum in the segment of the array. Usually the easiest one is to use sparse tables, but again, if you want to save the memory, a sparse table uses n-log-n memory. Yeah? So you may want to use segment trees just to save some memory, but it's up to you. So you use either sparse table or segment tree to calculate this minimum query. Now, all we need is to pre-calculate this array L. So when we have this array L, then we can answer these queries just taking minimum in this array. So how to calculate this array L? To calculate array L, there's very cool linear time algorithm. Let's just write this. Yes, you can use Farah complementary algorithm to answer minimum query in constant time using linear time memory. You can do it. Again, it's up to you. You can use any algorithm to calculate minimum queries, so depending on how much memory you want to use and so on. Again, we discussed it in the previous semester. I won't repeat. Now, how to calculate array L? I will discuss algorithm by Kasai, Arimuro, Arikavali, Pak. There are 5 scientists who actually discovered how to do it. There was another linear time algorithm discovered before, but this algorithm is very easy. So there is very easy and beautiful algorithm to build this array L. So how to build this algorithm? How to build this array? You just go and build it, starting from the longest suffix to the shortest suffix. So you take the longest suffix in your suffix array. So what is the longest suffix? Longest suffix is a suffix starting with character 0. So you take this suffix and just calculate the LCP of this suffix and the previous suffix. So you take this suffix and previous suffix and calculate the LCP, just comparing all the characters by one. So you compare this is equal, this is equal, this is not equal. So you say the LCP of this and this is what? Is 2. Yep. This would be array L. Easy, right? So you just compare the characters until you find different characters. Now you move to the next suffix, which is 1 character shorter. So we calculated LCP of character 0 and previous one. Now we take suffix 1, it's here, and calculate LCP of 1 and 2. Now, let's see. We have suffix 0. If we remove the first character from the suffix, we will get suffix 1. And before suffix 0, we have suffix 3. And if we remove first character from here, we will get suffix 4. So we know that there is suffix 1 and suffix 4. And since suffixes this 0 and 3 had 2 common characters, then suffixes 1 and 4 should have at least 1 common character. Yeah? So there is 1 common character between these suffixes 1 and 4. Again, we know it because we know there are two characters here. Let's put it here. So if we just remove this first character, we will get suffix 4 and suffix 1. They are here, suffix 4 and suffix 1. So these 2 suffixes must have this character B here and here. And it must be the same. What does it mean? It means that suffix 1 and the previous suffix also must have this one first character. Yeah. So we don't need to check the first character. We can start from the second character. So we start from the second character and compare starting from the second character. So we compare these 2 characters, see they are not equal, and just skip the first completely. And say that the answer here is 1. And so on. Now again, we move to suffix 1. Compare first characters. So this character is equal, this character is equal, not equal. Again, when we move from 2 to 3, we know that we have 2 common characters here. So suffix 3 and the previous suffix must have at least 1 common character. So we can skip this first character and go to the second. So we can skip this first character. And so on. Yeah, let me write it down here. So we had suffix I. And the previous suffix, for example, j. Like this. They have some number of common characters. So let's say we have k common characters here. And here we have some difference. So here has y, here we have x. So we already calculated the LCP of these two suffixes, and it is equal to k. So the result for these two suffixes is k. Now we move to suffix I plus 1. Suffix I plus 1 is the same suffix as 1 as I, but we remove the first character. So it's one character short, right? So we take this suffix, remove the first character here. It must be a little bit shorter. Like this. Let's look at suffix j. If we remove the first character of suffix j, we will get suffix j plus 1. So suffix j plus 1 is somewhere here. J plus 1. Now, we have k common characters here. If we remove the first character, we'll get k minus 1 common characters. So these suffixes I plus 1 and j plus 1 have k minus 1 common characters. And here we have x, here we have y. So the suffix j plus 1 must be above the suffix I plus 1 because it is less. Yeah, it is lexicographically less than this suffix. And they have k minus 1 common characters. Now again, all the suffixes between must also have this k minus 1 common character. So if we look at all suffixes here, they also must have this first k minus 1 common characters. So the LCP of this a plus 1 and the previous suffix must be at least k minus 1. But it can be more than k minus 1. So we just, so the character here may be y, for example. So we just continue to compare these characters one by one until we find the different characters. We just skip all these characters and start comparing from here. So we find the first character which is different again. Here we have A, here we have B. And stop there. That's the whole idea. So again, we just calculate the LCP from the longest suffix to the shortest suffix. When we move from suffix I to suffix I plus 1, if the LCP of I and the previous was k, and k is more than 0, then we can skip k minus 1 characters here and start from the next character. That's all. Now time complexity is linear. Why the time complexity is linear? Let's write it here. No, because each time we move from one suffix to another, we decrease this k by 1. And when we compare two characters, we increase k by 1. So we decrease k at most n times, and we. So no, let me write. So, okay. Let me write down the code. It's a little bit easier. So we just iterate all suffixes, right? From 0 to n minus 1. Then we try to calculate this. So we take suffix I, j, so. I kind of want to find the position, right? So suffix j is the suffix in position previous to I. Yeah. So I need to find suffix I, then find the previous suffix. J is the index of previous suffix. Yeah. Now k equal to 0. So k is the number of characters I already know I equal. Yeah. So now I just increase this k until I find the different characters. So while while character I plus k equals to character j plus k, I just increase this k. Okay, I just skip all the equal characters. Now the k is number of equal characters. So I just say that L of pos I equal to k. Like this. And now if k is greater than 0, I will like this. That's the whole code basically. So again, I take my suffix, take the previous suffix, greedily skip all the equal characters, now assign this value as LCP, and now move to the next stage. When I move to the next stage, I just decrease this k by 1, because if I know that like k equal characters, then on the next stage there must be at least k minus 1 equal characters. Yeah. So why the complexity is linear? No, the only thing is not linear is this while loop. So everything else is linear. In this while loop, we increase this value of k, so we find more equal characters. So we kind of increase the number of equal characters we already know. So in this while we increase the value of k. Yeah. Now in here we decrease the value of k, and the value of k can be more than n. So at any point k is no more than n. Because k is the number of equal characters. So here we decrease k at most n times. K can grow more than n, so we cannot increase k more than 2n times. Actually, no more than n, but doesn't matter. Good enough. So we cannot increase n more than n times. No, that's all. So everything else linear. It's similar to the Knut-Morris-Pratt algorithm a little bit, but not exactly. It's not exactly the same, but quite close. The idea of the time complexity is the same. So we have this while loop, but it's like two pointers method mostly. So in this while loop, we kind of extend this. So if you look at the string of the equal characters, in this while loop, we extend this string to the right, so we find more equal characters. And after the end of this loop, we decrease the case, so we remove the first letter. So we kind of, this string of equal characters is growing to the right and like shrinking from the left. So something like this. So it's more like two pointers method. So total time complexity will be linear. Whew. Okay, I think that's all.